fluids in motion and Bernoullis principle. Simple fluid motion is governed by two key equations. One is the mass flow rate, and the other is Bernoullis' equation. Let's focus first on the mass flow rate, which is also known as mass continuity. Let's consider a fluid that flows smoothly with no friction. This type of flow is called laminar flow. The mass flow rate is the mass it passes a given area per unit time, delta t. The mass flow rate must be the same as it crosses any area as long as no fluid is added or removed. So if we look at the diagram below, we see on the left a mass 1 crossing a larger cross-sectional area, and on the right we see mass 2 crossing a smaller cross-sectional area. We know that since nothing can be added or removed, these two masses must be the same. Let's look at mass flow rate in a little more detail. The mass that flows past any point or across any area is given by rho times v, the density times the volume that travels during that time delta t. We can write that as rho times a times x, where a is a cross-sectional area and x is the distance down the pipe that the fluid flows. Consequently, if we divide everything by delta t to find out the mass per unit time, we have rho a times x divided by delta t, which we know to be velocity or speed. So we have mass per unit time is given by rho times a, the cross-sectional area, times v, the velocity. Since the mass that flows past any point is given by m divided by delta t equals rho a v, we can see down here that because the masses are equal, rho 1 a1 v1 has to be equal to rho 2 a2 v2. If the fluid is incompressible, which we assume in all the problems we'll be doing, rho 1 equals rho 2, and our continuity equation, or mass continuity equation, is just given by a1 v1 equals a2 v2, where a represents cross-sectional area and v represents the velocity of the fluid. Just to conclude about mass flow rate, density does not typically change in liquids. This means that where a pipe is wider, the flow is slower. Where the pipe is narrower, the flow is faster. You can see this in a real-world example when you look at water flow through a river. The flow is slow when the river is wide and fast as it narrows.